In the previous section, we discussed some of the ways in which the Erdős-Renyi random graph model is not a fit to some real-world networks. In this section, we'll focus on the particular feature of the presence of hubs. These are extremely well-connected nodes that happen to occur in many real-world networks, but cannot be replicated with the Erdős-Renyi random graph model. Let's look at some of those real-world networks. Here is Sun's Java Forum, an online forum where individuals post questions and others will answer them. We see that there are many individuals who come in and ask, so blue denotes primarily asking, and some individuals will primarily answer, denoted in red. The size of the node denotes the degree. So here is a node who primarily helps, and is helping many low-degree blue nodes. There are some exceptions, so here are some blue nodes that have been helped by many others, and this node appears to both be helping and asking questions of others. We'll look at the degree distribution to see how it captures this uneven participation. Here I'm plotting the cumulative degree distribution, which means that, for example, if we look at having degree 10, say you have helped 10 others, this is the red curve, then we can read that there's a chance of 1 in approximately 100 that you have helped 100 or more people. This is what cumulative means. The probability up to here captures the likelihood that you have this degree or any degree that's greater. Now, we see that some individuals have helped thousands of others. If we look at the askers, there's still quite a skew in the degree, but perhaps at most an individual is helped by dozens of others. So, can we come up with such models? Would be good, because this isn't the only network that has such skew. So here is a network of reported sexual partners, and typically men will report having had more partners than women do, but in either case you can see a heavy skew with the majority of individuals reporting having a couple of partners and then a few individuals reporting having many. When we look at such a power law distribution, you'll notice that I used a log-log scale and that the distributions looked approximately linear on this scale. The reason why I did this is because if you use a linear scale that is not log-log, what you find is that you can't really distinguish, is the probability of having degree 20, is it 0 or is it different from 0? Similarly here for 50, right? It doesn't look any different than 20, which actually looks like, the value is 0. But if we replot this on a log-log scale, what we see is that the probability of having degree 50 is somewhere above 0.00005. Now this may seem like a very, very low probability, but if you have a network of 100,000 nodes, you would expect actually on average 5 of them to have exactly degree 50. So it's useful to know this, because you will actually observe these high degree nodes if your degree distribution is power law. And if you were to just look on a linear scale, you would have this L, which would obscure this relationship. So you typically want to plot your degree distribution on a log-log scale if you're dealing with networks that have hubs in them. On the other hand, when we looked at the Erdős-Renyi random graph, what we saw was a Poisson distribution, which is this approximation to the binomial. And here again, if we look at having degree 20 or having degree 50, these look pretty much like 0 again. And if we actually look up the likelihood that a node has degree 50, it's something like 10 to the minus 26 or 28 or something like that. It is puny. It is actually a true 0. So with an Erdős-Renyi random graph, here you would never see a node with degree 50 when the average is something more like 10. And so these two distributions are actually quite different. So we'll need a different model than the Erdős-Renyi random graph model if we are to explain high degree nodes. this power law distribution, because it's a straight line on a log-log plot, it ends up being a line. So if you take the log of the probability of having degree k, it's going to be equal to some constant minus alpha, this is the power law exponent, times the log of the degree. And if you exponentiate both sides, you get this relationship that the probability of a node having degree k is equal to some constant times k to the minus alpha. Again, this power law exponent shows up. Now let's see if you can answer this. As the exponent alpha increases, the downward slope of the line on a log-log plot, does it stay the same? Does it become milder? Or does it become steeper as alpha increases? Now, as I said, we need a new model. The Erdős-Rényi just isn't going to cut it. And we're going to need two ingredients. The first is that nodes are going to appear over time. If you think about social networks, this could be birth, or it could be someone joining a new workplace or a new school where they approach the existing network and then form social ties. If you're thinking about new publications, the new paper that is published is going to be citing previous papers that are already in the citation graph. So just to illustrate a little bit further, you have an existing network. And here's a node with no connections, and here is a node with 3 different connections. And now a new node comes in, and it has some fixed number of edges allocated with which it will attach to the existing graph. So does it want to attach to this node with 1 edge and to this other node with another edge? Well, in the preferential attachment model, what we'll see is that the node is going to prefer to attach to the existing node in proportion to the number of edges it already has. So it would be more likely to attach to, 3 times more likely to attach to this node, which has 3 edges, versus this node, which has 1 edge. Let's look at networks that are grown just with ingredient 1. So new nodes will join over time, but there isn't a preference that they have for joining to certain nodes and not others. The only restriction is that they have to link to someone who's already there. So for example, each node might come in with 2 edges. What this means is that by time t, you have t nodes, 1 joined at each time step. It also means that at time t, when that new node comes in with m edges, each existing node is expected to increase its degree by m over t. That is, it's competing with t other nodes in the network for m edges. This also means that over time, the older nodes who have been around longer are going to accumulate more edges just by having been around. So if node I was born before node j, we would expect on average that the degree of node I is greater than the degree of node j. Because this is a random growth process, that need not always be true, but it typically is. So how could one make the growth model more realistic for social networks? Should old nodes die? Should some nodes be more sociable? Should friendships wane over time? Or perhaps all of the above? I hope you picked all of the above because even though mathematically it becomes more difficult to solve such models, they capture many of the realities of networks. So in social networks, individuals tend to leave one way or another eventually. In citation networks, older papers may lose interest over time, or maybe for the best ones, their results become so ingrained that one doesn't even cite them. It's just known as a general truth, part of our knowledge base. Maybe some nodes are more sociable. Why should everyone have the same number of edges? Maybe some individuals form more ties simply because of an intrinsic property. Friendships might wane over time. Why do you have to keep all the edges you had in different contexts from a long time ago? And you can probably think of many other ways in which you can enrich such models. Now let's turn to the second ingredient, which is that of preferential attachment. Here, we're going to, when the new node comes in, it's going to want to connect to the popular kid and not to the less popular kid, or the loner. And this process is also known as cumulative advantage or rich get richer or the Matthew effect, meaning that if you already have a lot, you're going to get even more. And here we're talking about edges as being the wealth. This model was first introduced by Price, who was modeling how papers get cited, and it has been observed for a long time that some papers are just cited a whole lot more than others. And here, rather than having the probability of attachment directly proportional to the degree, it's going to be proportional to the degree plus 1, which is going to take care of a cold start problem. And that is that if a node has degree 0, it would mean that in proportion it would never get cited. Of course, this isn't the case. Papers, all start with 0 citations and then eventually accumulate them. This kind of process will give you a power law exponent alpha of 2 plus 1 over m. And this tends to be in good agreement with many of the observed empirical distributions. Just to look at this image again, so we have a new node coming in. It could cite the paper that hasn't been cited at all, or it can cite the paper which has lots of existing citations. And it's going to prefer to cite to this one in greater proportion than this one. How does this actually happen? Well, there could be many underlying mechanisms, but one of them is copying. So if you're reading one paper, you might actually look through its references and find that it cites another paper. And so you copy the citations of others. And because that existing paper you're reading is more the paper that it's citing has higher degree by virtue of the fact that it's being cited, you're then more likely to cite it as well. So it's a cumulative process. It may also just be that more highly cited papers are just more visible when you search in different databases. It may show you the more highly cited papers first, which again would give such papers an advantage. The more recent and very widely known model is the Barabási-Albert model, which was first used to model the skewed degree distribution of the World Wide Web. And in particular, László Barabási and Réka Albert were looking at the Notre Dame website and noting that some of the web pages had many more edges, that is links, than others. And they considered an undirected model, even though in reality the web is a directed graph. So the process is going to start with some initial subgraph. It could be a fully connected clique of a few nodes who all link to each other, or maybe it is just a circle. And each new node is going to, again, come in with m edges, and the probability of connecting to node I is going to be proportional to the degree of node I. That is, it's going to be proportional to k sub I. And this is going to result in a power law with an exponent alpha of 3. 3 is a bit high for, it's a bit higher than most of the observed power law distributions. However, one can modify the model in interesting ways. For example, giving the nodes different fitness or some intrinsic attractiveness, such that you might prefer certain nodes even if their degree initially is lower, and this will produce more realistic power law distributions and exponents that are closer to 2 than they are to 3. But let's see what it looks like with the pure Barabási-Albert process. After a while, you will see some hubs emerge. Here the nodes are sized in proportion to their degree. And we can contrast this with the random growth. Even with random growth, we had some nodes typically the older nodes who had higher degree, but there wasn't as much of a disparity between the best connected nodes and the least well connected nodes as there is in the Barabashi-Albert model. So again, this is the preferential attachment and random attachment, and both have the same growth mechanism in that nodes join one by one over time. So just to review, we have the properties of the Barabashi-Albert graph, a power law exponent of 3. We have that the graph is connected because we start out with a connected graph and every subsequent node is going to attach to an existing node which itself has attached through some chain to some of the original graph. We also have that the older here are richer, and if you track the average degree of a node born at time 5 versus one that was born at time 100, that node that joined later, it's going to have a really hard time ever catching up to the node that had the advantage of being there early. Now, this is not entirely realistic either. If you look, for example, at the oldest websites, some of them are still around and popular, but many of them never got a huge following, and that is because over time there's some fitness to the different nodes. Some websites grow very, very popular and others wane in popularity, and it's not all about how many existing edges they have. Next, I'd like you to explore these growth models yourself. Let me find the NetLogo model. What you're going to do is you're going to start out with just 2 nodes which share an edge, and you have this slider, which is the probability that a new node which comes in is going to attach preferentially in according to the degree of the existing nodes, or maybe it's just going to attach at random. So let's first start with random. And I'm going to click go, and this is going to be a little bit slow, so I'm going to speed it up. Maybe stop once we have about 250 nodes. So there you go. You have the degree distribution both on a linear scale and on a log-log scale. And you also have the ability now to change to preferential attachment. I'm going to set up and say go, and stop at a similar number of nodes, 250, and hopefully already visually you can see that the structure is different. You can see the hubs here. You can also see the difference in the degree distribution. So going back, we have our next quiz question, which is relative to the random growth model, the degree distribution in the preferential attachment model, does it resemble the power law distribution less or more? Hopefully you got that it actually is more power law than the random growth model, which tends to have an exponential cutoff. And we know that actually this should match the Barabashi-Albert model and that the exponent is 3. The power law exponent is 3. However, it's difficult to tell that from the NetLogo graph, but there are ways of fitting such distributions and deriving the exponent, which is something that I'll cover in an extra advanced segment next week in case you're interested. So to summarize, we talked about growth models because networks aren't born, they're made. They evolve. Nodes are added to the network. Edges are added to the network. And we saw a couple of properties of these very basic growth models. The first is that because nodes join over time, if a node is older, it's more likely to have accumulated edges. But the true hubs you get when you have preferential attachment. That is, it isn't enough for the node to just kind of lie back and wait for edges to come in. The new nodes have to prefer a well-connected node. So for example, a new kid joining a school will want to hang out with a popular kid as opposed to the loner. Or a new paper will want to cite the well-cited paper as opposed to some other paper that hasn't been cited at all, or it might do so accidentally, not accidentally, but it's reading another paper, and so reading through those citations, it's going to end up copying some of them and so citing already well-cited papers. Okay, in any case, once you have this kind of preferential attachment, you're going to have the formation of hubs. Now, in this week's assignment, I've left a lot of the fun kind of out of the lecture and put it into the assignment. So even if you're just following the lectures without taking the course for credit and you're not doing the assignments, really you should do this assignment because it's going to show you why modeling is important. That is, we're going to look at these different models and you're going to be able to tell what the effect of the different growth mechanisms is on the ability for an infectious agent to spread. So this infectious agent, it could be a bacterium, it could be information, and you're going to look at different aspects. So the first is going to be the distribution of component sizes in the network and how this impacts how far the virus, for example, can spread. The second thing you're going to look at is in growth models, whether the growth is random or preferential, whether that impacts the speed with which the infection can spread. So I think that actually is like kind of the other half of what we should be learning this week, which is not just that these models can explain the structure of the networks that we see around us, but that having these models, we then gain insight into how different processes might then occur differently depending on how the network grew or came to be. So I hope you will find that fun, and I'll see you next week.